Hello again. So now we're going to talk about line integrals. So in the last video we talked about vector fields and some of their derivatives, right? You can take the derivative of a vector field in a number of ways. You could take its divergence or its curl. Those are sort of derivatives of vector fields. So now we're going to take their integrals, so to speak, and they're called either line integrals. Some books call them contour integrals or path integrals, although there's another context for path integral that is way more advanced than what we're going to talk about. But yeah, so I'll just call them line integrals, even though that is a bit of a misnomer. It doesn't have to be an integral over a line. It could be a curve, right? Or a circle. Or, yeah, it could be any curve, right? So a line is considered a specific type of curve. So going back to curves, we know what a curve is, right? Usually it's given parametrically. Let's say this is a curve in space, right? So r of t is the, you can think of it as the position at each point on the curve. So a curve is called smooth if the derivatives of x, y, and z are all continuous and not equal to 0 for any t on the interval from a to b, right? And the same t for both, right? So this was usually expressed as just saying that the derivative of r at any t is not the 0 vector, right? So yeah, that's the key condition here, right? And all that means is that right, the curve doesn't have any turns to it like this, right? So at these points, of course, it would not be considered smooth, right? Right, because what would happen, right, at this point is either the derivative would have to suddenly change or it would have to be 0 there, right? And we saw earlier that can happen even if the curve looks like this, that the parameterization may not be smooth at a specific point. So we can't tell by looking at the curve whether the parameterization is smooth or not. It depends on the x, y, and z, right? But we're not going to get into that. Yeah, so a smooth curve, right, just looks like this. But in some cases, we're going to be dealing with curves that are not smooth, and yet we would like to deal with them, even though they're not smooth. So then we have this idea of the next best thing, and it's called piecewise smooth. A piecewise smooth curve is basically just a curve that's divided into smooth pieces. So let's see if I can do this right. Right. So you have a square. Obviously, a square is not smooth because it has these 4 corners at which the curve would not be smooth, right? Fair enough. It's not a smooth curve. On the other hand, each of these line segments is smooth, right? And so it is considered piecewise smooth. It's just four smooth pieces, right? So even though this is not smooth, right, it is definitely piecewise smooth, right? And then the idea is we'll just divide it up into the 4 pieces, right? So yep, you can say the same thing about a triangle is not smooth, but it's 3 smooth pieces, right? So so the figure I drew earlier, something like this, right? That would be 3 smooth pieces. They don't have to be straight, right? You might have a figure that looks like this. Suppose I have, say, half a circle, and then a straight line, and then another half circle, right? So these are 3 pieces that are smooth. They don't have to be straight. So you have the straight piece here, and then you have 2 curves or 2 arcs that are definitely smooth, but the entire thing together is not smooth. It's piecewise smooth. Okay, so that's what it means to be piecewise smooth, right? Okay, so here's our first example. We have this triangle here. So again, not a smooth curve, so it is a right triangle, obviously. And the idea is to parameterize it. So let's say we want to parameterize this curve. I'll just call it C. I should call it T for triangle, but you know, it's just a curve, right? And it's a closed curve. It's a curve that closes on itself, right? So this is the hard part, is coming up with a parameterization, simply because it's not one smooth curve. It's three pieces of a smooth curve, right? So three pieces. So we essentially just have to parameterize each piece in such a way that we want the entire curve to be, continuous. Okay. So we can start anywhere along this triangle here. I guess I would start at the origin, 0, 0. And you can see by the arrows, I mean for this to go around, counterclockwise. So that's what's called the orientation. So I think we talked about that a little bit back in chapter 12, but if not, we'll do it again soon. So this is just going around counterclockwise, right? So our first piece is just from the point 0, 0 to the point 2, 0. Right, so that should be pretty easy. Right, so I'll just call this R1. Right, we can just, since y is 0, it just depends on x. So let's say x is just t. So we can say we can say it's just t0, or ti plus 0j. Right, and then t just goes from, say, 0 to, well, it would have to go to 2 here because we want to end at 2, 0. Or let's say we want to end at 1, t equals 1, then we just have to go twice as fast, right? So we multiply by 2, 2 times t, right? So now if t is 1, right, you can check that when you plug in 1, you just get the vector 2, 0, which is the position at the point 2, 0 as a vector this time. Okay. So that's the first piece, and that's usually the easiest, right? But now the second piece. This gets a little trickier, right? So let's think about just the x's and y's individually here. What is x doing? X is going from 2 to 0, right? So x is going from 2 back down to 0. But t, on the other hand, we can't go backwards. We can't go from 1 right to 0 because, well, 0 is not bigger than 1. So we want to go, say, from t equals 1 to t equals 2. All right. So let's just think how we can do that here. How can we describe x? Well, since we want x to be decreasing, I would start with just multiplying t by a negative, right? So now if t is 1, this is negative 1. And if t is 2, this is negative 2. So it is decreasing, but we're not going from 2 to 0, right? So same problem here. If we want to go, say, from t equals 1 to t equals 3, that might work better. On the other hand, if we insist that we want to end at t equals 2, we might have to multiply this by negative 2, right? So now we're going from essentially negative 2 to negative 4. But we want to go from 2 to 0, right? So if I just add 4 to that, right, and t is 1, 4 minus 2 is 2, right? And 4 minus 2 is, or 4 minus 2 times 2 is 0. So, right, so that should do it here for x, right? If t is between 1 and 2, right, then x of 1 is 2 and x of 2 is 0. So x goes from 2 to 0 as we insisted, right? Okay, so that'll be the x component. Just 4 minus 2 times t here, right? All right, what about the y component? The y component is going from 0 to, well, 4. This is the point 0, 4 here, right, at the top. So, so the y just goes from 0 to 4. Right? So we probably should just multiply t by 4, right? So 4 times t. But that would work, right, if we're starting at 0 and going to 1. Right? But we're starting at 1 and going to 2. So I think we're just going to have to take away 4 from that. Well, the way I was thinking about it is it's 4 times t minus 1, right? Because now if t is 1, y is 0, and if t is 2, y is 4, right? So that's the same thing as 4 times t minus 4, right? And you can check that. So, yep. So, yeah, I'll just write it as 4t minus 4, I guess. Right. And, yeah, t, right, so here t is going from 1 to 2. Right. I won't write it with the I and j. It's, you can do that. All right, and then the third piece is going from, let's see, x equals 0 to x equals 0. Well, that's easy. Then x has to be 0. It doesn't depend on t, right? The y is going from 4 down to 0. And remember, we want t to go from, say, 2 to 3. Okay, so because y is decreasing here, we're going to need another negative sign, right? So negative 4 times t, again, for the 4 seconds. But this would be going from negative 8 to negative 12. So what do I need to add to negative 8 to get to 4? So negative 8 plus what is 4? It's got to be 12, right? So we're going to add 12 to this. And that should do it. Now when t is 2, you're at positive 4, and when t is 3, you're at 0. So there you go. That's the parameterization. Now, obviously, it's not a single function here. It's 3 functions, right? But this is what you mean by a piecewise smooth curve, right? Your position function will depend on which piece you're on, right? So it's just going to be, I guess I'll go back to the I and j, 2i, if t is between 0 and 1. 0 is not working. There we go. And it's going to be, well, the most complicated piece, I think, is 4 minus 2t for x. So that's times I. And then 4t minus 4 times j. And that's if t is between 1 and 2. And finally, we just have 0i and then minus 4t plus 12. Or if you prefer, 12 minus 4t j. And that's going to be true if t is between 2 and 3. So that is the parameterization for this triangle up here, right? So yeah, this takes a little bit getting used to. Again, if you want to make this a little more precise, or maybe just, you know, a little more exact maybe, where we're not just guessing, well, what should we multiply by t? What should we add? You can do it just by, picking your t, say a. Oops, so let's say a is t, right? We're starting at a, ending at b, and that's our point, and we're ending at, say, when t is b. Oops, that should be a b then. Right. And of course, because this is just a straight line, you can just interpolate between the two endpoints. Right? In other words, just use, your y equals mx plus b. Or in this case, y equals m times t plus b. And just figure out your m and your b. Not the same b, right? So maybe, mt plus d or something. In any event, that's right. Because these are just straight line segments, I should say, these are just going to be linear functions of t, right? Right. So that works when you have straight lines. Obviously, when you have like a parabola, you might have to use t squared, right? So So just keep that in mind. Or if you have a circle, of course, you use your usual sines and cosines. All right. So again, this parametrizing these piecewise smooth curves takes a little bit of practice. And of course, there's a couple of these in the homework. So I think I'll leave it at that. In some cases we may need to use 4 pieces, like for a square up here, right? Then there would be 4 pieces, right? And so on, right? So it depends on how many pieces. Obviously, if you have, an octagon, which is 8 sides, right? Like a stop sign, then you're going to need 8 pieces. Oh, I messed that up. Right. So then you're going to need 8 pieces. But trust me, I would never make you do that. That just takes way too long. But 2 or 3 or 4 pieces is reasonable. 5 or 6 is really stretching it, and certainly 8. To have 8 functions here is a bit of a nightmare. It's a little bit hard to do, or just very tedious to do. Okay, so you're not going to have to worry about things like that. But squares and triangles and rectangles and circles, or maybe half circles, like if you have a half a circle and then the straight line. So let's say we start over here, that's our point A, and we go to point B to the right, and then we go around the circle counterclockwise and we end up back at point A again. So this is only 2 pieces. One piece is a line, or a line segment, and the other piece is, half a circle. So for the circle, you'll use your sines and cosines, and for the line, you'll just use some linear function of t. Got it? Okay, so now we can talk about the line integral. So consider a wire, like a metal wire, bent into this shape here, the shape of the curve C. And it's a finite length wire, right? So it starts at point A, it ends at point B, right? Suppose the mass density at each point on the wire is given by this function. I'll call it rho. I know I go back and forth between sigma and rho. Again, the book likes rho. So, okay, so rho is the density at each point, right? And I know this is a curve in a plane, but it could be a curve in space as well, right? So if we were to divide this wire up into a bunch of little pieces, right, like this. Each piece, of course, is not exactly straight, but if you just say, look at this piece right here, and let's blow it up even more. Right? So no, it's not exactly straight, but it's pretty close, right? And the point is you can divide them up smaller and smaller, and the smaller you go, again, once you blow it up, it's going to look more and more straight, right? So yeah, even though this piece here is not exactly straight, it's not far from being straight, right? Right. So each piece then, let's say has length delta s, and let's say this is the ith piece, right? So I goes from 1 to n, if there's n pieces, right? And so if you multiply, I'm calling it f here. I guess I should call it rho. If you multiply the density times the length, right? So this is the linear density, right? So I really should use lambda, I suppose, but the book likes rho. Right? So if I multiply the density times the length, this then represents the mass of the ith piece, right? So just that little piece right here, that's the mass of that piece, right? It's the length, delta Si, times the density, right? Because density, well, is just the mass divided by the length. So if you multiply by the length, in this case, delta S, you get the mass, right? Okay, so now just take all the pieces and add them all up, right? Add the mass of all these pieces, right? And again, there's n of them, so we have to do, sum going from 1 to n, right? Right. So that will be the approximate mass, but if you want the exact mass, you take the limit, right? As the norm of the partitions goes to 0, effectively as n goes to infinity, right? So you divide this up into more and more pieces until there's infinitely many of them. And when you do that, then you get something called the line integral over the curve C of the density function times ds, right? That's what happens when delta s goes to 0, you get ds, right? So this is an example of a line or contour integral. Right? And now we instantly know what it represents, right? It represents the mass of the wire, right? Okay, so that's the interpretation, right? Each little piece has its own little density. So if the density is not uniform, then you need to do an integral. Obviously, if the density is the same at each point, right? If the density is just a constant, right? If it's just constant, then there's no need to do an integral. You just multiply that constant rho times the length of the wire L, right? But if the density varies, then you're not just multiplying, you're doing this line integral. Okay. So first of all, what is this ds? Remember what s is, right? S is the arc length, right? And so we can think of ds, right, as just the length of each little tiny piece, right? And in particular, if you remember what ds over dt was, that's like the velocity, right? Distance over time. Well, not velocity, because it's not a vector. It's the speed, right? It's the magnitude of the velocity, right? So in other words, if I parameterize this curve as r of t, then ds over dt is just the derivative of r, and then you take the magnitude, right? So we can write ds as just the speed times dt. Right? Yeah. And as a special case, right? As a special case, if this density function, let's just say it's a number. In fact, let's just call it 1. Right? If the density is 1 at each point, then what do we get? We get the total length, right? S, the arc length of the entire curve, or the wire, right? So yep, you're just adding up all the lengths of these little pieces, and you get the total length of the curve, right? Okay, so that's as a special case if rho is equal to, say, 1, right? Or if rho is constant, then it's the constant density times the length, which means it's the mass again. Okay, so now how do we actually calculate these line integrals, right? So instead of using rho, I'll go back to just some generic function, f, as a function of x, y, and z, right? So how do we calculate these line integrals, right, in practice, right? So yeah, so the idea is to parameterize the curve, right? So we have to parameterize C, right? And in some cases, it might be given to you as parametrically. If not, you just have to parameterize it like we did with the triangle, right? And the triangle is a piecewise smooth curve. So this can happen for a smooth curve or a piecewise smooth curve, right? So after we parameterize C, we have our parameterization, say r of t, right? And remember, r of t is just, x of t I plus y of tj plus z of tk, although I didn't write it that way. It's just a vector representation, right? And if you're going from point A to point B, let's say t goes from little a to little b, right? So then we can express this line integral as an actual definite integral from t equals a to t equals b, right? And then we have our f of t, because remember, x, y, and z all depend on t. So if you rewrite x, y, and z in terms of t, then your function f is a function of t instead of x, y, and z. And the ds, remember, is just the magnitude of r prime, that's the speed, times dt. So now this is an integral with respect to t. Again, you can think of t as time, but in general, it's just some parameter. Right? And so that's practically how you do it. Right? So this is a theorem in the book, so we're not going to prove it, but that's the idea. Or, you know, as a practical matter, this magnitude of r prime is just the following, right? So we still have f of t, and then this is just going to be the square root of the derivative of x squared, right, plus the derivative of y squared. And that's it if it's a plane curve, but if it's a curve in space, then you, of course, have to add the derivative of z squared, all times dt, right? So that's what the magnitude of r prime is, practically speaking. Okay, so now our next example is we're given a curve. In this case, it's just a line or a line segment, right, from the origin 0, 0, 0 to the point 263. And we're also given the function f. Again, we can think of that as maybe the density, right? And then the line integral that we want to calculate or evaluate, the line integral, that will represent the mass of the wire. In this case, just a straight wire, right? So how do we evaluate this line integral? Right. Well, remember, the first step is we have to parameterize C. So parameterize C, the curve. Right, so you're just going from point A, 0, 0, 0, to point B, 263, along just this straight line here. Right. So yeah, if it's a straight line, remember the parameterization should be pretty simple. Since we're starting at 0, 0, 0, we don't have to, you know, subtract or add anything to the t. If we want x to go from 0 to 2, why don't we just multiply t by 2, 2 times t, right? So in other words, we're going from t equals 0 to t equals 1. Now the y is going from 0 to 6, so that's going to be 6 times t. And then z is going from 0 to 3, so 3 times t, right? That should do it, right? As a check, if we plug in t equals 0, we just get the vector 0, 0, 0. That's the starting point, right? And if we plug in t equals 1, we get the vector 263, which is the ending point. So that's exactly what we needed, right? Again, for a straight line, it's usually pretty simple. Right? Okay, so that's the first step, right? Now the second step is, well, we want to evaluate this line integral, right? So what we need to do is rewrite the function f in terms of t, right? Because t is going from a to b, or in this case, 0 to 1, right? A is 0, b is 1. Right? All right, so, so this is, f is the function. Oh, I can't do that yet then, can I? A little premature. So this is still the curve C. But the function f is given above, right? It's 3x squared plus y squared plus 2z squared ds, right? Okay, so that's just replacing f with the given function here. Right. Now we can parameterize, or we parameterize the curve, so t is going from 0 to 1, right? And remember what x is just 2 times t, right? And y is 6 times t. And z, right, 2 times z squared, so z is 3 times t. And that's it. Oh, sorry, not dt. Remember, this is ds. So remember what ds was. It's r prime, magnitude of r prime. So yep, to get ds, right, we need to take the magnitude of r prime of t. So r prime, of course, is just the derivative of each component, right? So it's 263. And the magnitude of that is the square root of 2 squared plus 6 squared plus 3 squared. And it looks like the square root of 49, Well, that's nice because that's just 7, right? So that's ds over dt, right? So ds is really going to be the magnitude of r prime times dt, which in this case is just 7 times dt. So the ds is 7 times dt. Right? So that was our ds. Right? Yeah, and so we're almost done. The 7 is a constant. I can bring that outside. And now we just multiply everything out here. This is 3 times 2 squared, so that's 12t squared, right? Plus 36t squared, plus 9 times 2 is 18t squared dt. So, yeah, 12 plus 36 plus 18 is 66t squared dt. The 66 is a constant, so that can come outside. And I'll multiply the 7 and the 66 in a second. But now we're just integrating t squared, right? Okay, so 66 times 7 is 462. Okay. And now we just do this definite integral. The integral of t squared is 1/3 t cubed, evaluated between 0 and 1. So 462, divided by 3, and, times 1 cubed minus 0 cubed, but that's just 1. So 462 divided by 3 is 154. Okay, so that's the line integral. That's the answer, right? You get a number, 154. So what does that number represent? Well, again, it depends on your interpretation of, right? So all we're doing is we're adding up the values of this function at each point on the line segment. Remember, the line segment was up here. So at each point on this line, right, f will have a different value. You plug in the specific x, y, and z on the line, and you plug that into the function f, and you get a number. And then you just add up all those numbers along this line segment here, right? Right. So if f is the density, then the 154 would be the mass of that wire. Right. So I didn't give units, so it could be kilograms, it could be milligrams, it could be ounces. So 154, whatever units of mass, right? So that's the interpretation if f is the density function. But f is just some generic function, so the answer is 154. Right, so again, a pretty easy example to start, and maybe we'll do one more that's not so easy. Okay, so here's our next example, and it's actually not any harder than the last one. It's, to be fair, it's kind of hard to come up with a really hard one. But in this case, I don't think it is. Or maybe it is. Maybe it isn't easy. To be fair, I just made it up. So I actually don't know how this is going to go. So first of all, our curve is already given parameterized. So we don't have to parameterize it. It's already given that way. And just to be fair, right, if x is t squared, then y is going to be, the square root of x, right? So right, we're going from 0 to 3, so y goes from 0 to 3, x goes to 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so the curve is just this parabola, right, sideways. Right, we're starting again at the origin, 0, 0, and we're ending at the point 9, 3. Right, and we're going this way. So that's our curve C. It's given that way, right? And we're also given the function f, it's just xy cubed. Right, so now we just want to evaluate this line integral. All right, well, so the way to do that is f, of course, is just xy cubed times ds. So we know t varies from 0 to 3, and x is just t squared, and y is just t. But remember, it's y cubed, so it's t cubed. Right? So that'll be t to the 5th, right? And now ds, right? ds is, well, we have to take r prime, which is just 2t, 1. And now the magnitude of that, oh, I was afraid of that. So it's going to be the square root of 4t squared plus 1, right? And so your ds is just going to be the square root of, I'll do 1 plus 4t squared, same thing, times dt. So, yep, that's what's going to make this not so easy. But that's what happens when you just make up a problem like this. So yeah, we're going to get t to the 5th times the square root of 1 plus 4t squared dt. Yep, so that's our definite integral. And to be fair, it's probably just a substitution, I think. Let's try u is just 1 plus 4t squared. Right? Then du, of course, is 8 times t dt. The problem is we have too many t's here. So that means we have to solve for t. 4t squared is u minus 1. T squared is u minus 1 over 4. And so t is just going to be the square root of u minus 1 over 2. Ooh, so that's not exactly pleasant either. So if we raise that to the 5th power, what do we get? We get 1 over 32, and then we get u minus 1 to the power 5 over 2. And then we just get the square root of u. Right? Yeah, so we still have u to the 1/2 here. Oh, and du is, yikes, 8 times t. But t is going to be another u minus 1 to the 1/2 over 2. Right? And then dt. Yeah. Or wait a minute, I think I got that backwards. Right, because dt is, yeah, dt is 1 over at times du. So I think we got to flip this over, right? Yep, my mistake. Yeah, times du. All right, give me 1 second. There we go, right? So 2 over the square root of u minus 1 times 1 over 8. So that's 1 over t, right? All right, so just kind of a mess here. So 2 over 8 is just 1 over 4. And 4 times 32 is 128, I think, right? 64, 128. So this will just be 1 over 128 times the integral. And again, I didn't figure out what u is yet. U goes from 1 to, let's see, 3 squared is 9. 9 times 4 is 36. 36 plus 1 is 37. So u is from 1 to 37. Alrighty, that's not looking good. All right, and then u minus 1 to the 5/2 divided by u minus 1 to the 1/2 is just u minus 1 squared times the square root of u. And, yep, there should have been a u at this point, du. Okay, it's just a lot of algebra at this point. Because it looks like we're just going to have to multiply all this out here, right? U squared minus 2u plus 1 times u to the 1/2. Right, so we're going to get u to the 5 over 2 minus 2u to the 3 over 2 plus u to the 1 over 2 du. Right, so now it's just the power rule and the sum rule and all that stuff. So I'll leave the 128. So this will be 7 over 2, right? So 2 over 7, u to the 7 over 2, minus 2 times 2 over 5, so 4 over 5, u to the 5 over 2, plus 2/3 u to the 3/2. And yeah, oops, sorry, not 0, but 1 to 37. Okay. Again, we'll do the 128 later. At this point, of course, you just plug it in your calculator. And here's what I got, right? So when you plug in the 37, my calculator just approximated, of course. So 81,519.677. And then when you plug in 1, I forgot what you got exactly, but it's about 0.152. So divide by 128, and it's about it's about 636.871. So yeah, it's just a tedious, definite integral here. And to be fair, you could have just plugged this in your calculator to get that, right? I mean, your calculator will do definite integrals. I just figure I've been working these out by hand pretty consistently. So it's a nice review of, Calc 1 or Calc 2, depending on when you did substitution. All right, so that's another line integral. Right, so now we're going to consider a particle moving along a curve C that's given parametrically. And so we can consider, right, r to be the actual position function of this particle, right? Right. So suppose that each point on this curve, right, there's a vector. Say at this point we have this vector. I'll call it f. At this point we might have this vector. Again, it's f, but it's obviously it's a vector field, right? So yeah, each point you have a different vector, right? At this point you might have, say, this vector f here. At this point you might have this vector, and so on, right? So there's a vector field in space, and of course the vector field might exist outside of the curve. There might be vectors everywhere, say on the plane here. However, if we're restricting ourselves to the curve, we only care about those vectors, right, on the curve itself, on C itself. So we can ignore all these other vectors here, which means I probably should have not drawn them. But just keep in mind that when you express a vector field as a function of x and y, your x and y could exist anywhere in space, but we're going to restrict ourselves to the vector field f only along the curve, at least for the moment, right? Okay, so what might this vector field represent, right? It might represent some force, right? Like a force field, like, it could be gravity, although gravity would just be, a constant vector field, right? It would be straight down and in the vicinity of the surface of the Earth, right? But yeah, in general, it's just some force, right? So if you want to move the particle, right, let's say the particle starts at point A here, and you want to move along the curve to get to point B here, so starting at point A, ending at point B, right? How much work does it take to move the object from point A to point B, right? Because it's going to take work, right? You're moving a force through a distance, right? Remember, force times distance is work, right? Except here, it's way more complicated because we're not moving in a straight line, right? And the force is not moving in that same line, right? That's, work is force times distance, right? The force might not be in the same direction. And we talked about that earlier. When that happens, it's the dot product, right? It's F dot, the displacement vector, we'll say r. Okay? But that's assuming that the force and the displacement, are the same everywhere, right? That this force does not change along that line. Here, in this example, the force is obviously changing. It's not just changing magnitude, it's changing direction too. Okay? So to calculate the work, right, we're going to have to do another line integral. It's going to be the line integral over the curve C, right? Now remember, a line integral is a scalar function ds. So if we have a vector function, what does that mean? Well, we can take the dot product of f dot, not ds, ds is also a scalar, but we can do f dot, let's say, r prime times dt, right? Of course, r prime might vary the speed, so we really want to divide by its magnitude to just get a tangent vector, right? In other words, all we're really doing here is taking the force dot t, where t is the unit tangent vector, ds, right? So remember, t is just your unit tangent vector. Okay, right. So this would represent the work done. And it is a line integral. It just might not look as familiar, right? And again, as a practical way to calculate it, we're going to change s into t here. So we're going from t equals a to t equals b. We still take the vector field, but now as a function of t instead of a function of x and y. So maybe I should have made that clear, that f is a function of x and y, right? And you take the dot product with t, which of course varies with little t, with the parameter, right? And in fact, t, capital T, that is, the unit tangent vector, right? We already said what that was, right? It's r prime divided by the magnitude of r prime. But remember what ds is. ds is the magnitude of r prime times dt. So we get this kind of happy coincidence here. We can cancel the magnitude of r prime. Right. And so when we do that, we now have, we now have a definite integral from a to b. Remember, we have to express f as a function of t now, instead of x and y. And you just take the dot product with r prime of t times dt. Right? And in fact, a lot of books just write this as dr. Right? So dr, whenever you see dr, just think r prime dt, because remember, r prime is the derivative of r with respect to t. So times dt, well, cancel the dt's, and there's your dr, right? So, yep. So r prime times dt, or just dr. And so, yeah, so a lot of times we will see this line integral over the curve C as just f dot dr. But as a practical matter, to calculate it, right, you go from your parameterization r, starting at a, ending at b, right? And this becomes a vector field f as a function of t, right, dot r prime over dt, right? Right. So that's how we're going to evaluate these line integrals. And again, these line integrals represent work if f represents a force. Otherwise, you know, f could just be some generic vector field, and this is just some generic line integral. So this is, right, definitely a line integral. Or contour integral, path integral, right? Obviously, this is not a line, but we call it a line integral nonetheless. All right, so yeah, let's do an example of this now. Okay, so we have our vector field f. The x component is x plus 2y. The y component is y squared, x squared times y. And the curve is given, it's y equals x cubed. But, you know, instead of starting at 0, 0, like we usually do, we're starting at -1, -1, and we're ending at the 0.28, right? 2 cubed is 8, right? So here's the little graph of the curve here, right? And I'm not going to try to draw the vector fields, right? So, you know, just imagine a picture where at each point on the curve you have a vector field, right? But it's going to be pretty difficult to graph this one. And we want to evaluate this line integral here, right? The line integral of f dot dr. Remember, f is the vector field, and dr is essentially dr is just a little tangent vector at each point on the curve, right? Okay, so let's just do this, right? So remember, t goes from, well, we didn't parameterize the curve yet, I guess, so we have to do that. Right? They gave us the equation, y equals x cubed, so based on that, I don't see why we don't just do x equals t and y equals t cubed. Right? So then t goes from, oh, not 0 anymore, t goes from -1 to 2. Right? Because remember, t is x, x goes from -1 to 2. Okay, so that's parameterized, and remember, it won't be long before we need dr, so that's r prime. So that's just 1 3t squared. Nope, not times dt. Yeah, we'll multiply by dt later, right? But this is dr over dt. Right, and then we'll multiply by dt in a second, right? All right, so yeah, so we're going from -1 to 2, and f, the vector field, is, again, x plus 2y, and x squared y for the y component, and we're taking the dot product with r prime, which is 1 3t squared times dt, right? But you can see the problem here. This is not expressed in terms of t, so to do that, well, we know what x is. X is t, if it helps, right? X is t, and y is t cubed. So the x component will be t plus 2t cubed, and then the y component will be t squared times t cubed. It'll be t to the 5th power. So then we take the dot product with 1 and 3t squared times dt. So remember the dot product, right? So it's 1 times t plus 2t cubed, and then it's t to the 5th times 3t squared. Wow, that'll be 3t to the 7th. All right, well, at this point, it's just an ordinary, definite integral. So as I mentioned many times, you're welcome to just plug this in your calculator. But as usual, I'm going to work it out by hand. 1/2 t squared, right? This is 1/2 t to the 4th. And this will be 3/8 t to the 8, evaluated between -1 and 2. Right, now that I will do on my calculator, as you're welcome to do that too. Okay, so I decided to work it out by hand, and I'm not even sure it's correct, but this is what I get, right? 837 over 8, or 104.625. So what does that number represent? Well, it represents, right, if F is the force, right, the force field, right, it's a field of force. At each point you have a different, vector representing the force. And you're moving the point along the curve. It's essentially the work done by the vector field to move the object in that direction. So, yeah, maybe I wasn't clear here. If F is the force field, right, this is the work done by the force. It's not the work done by you against the force. That would just be the negative of this. So, yeah, so this is the work, this is specifically the work done by the force F, right? So if F is gravity, this is the work done by gravity, right? It's not the work done by us moving the particle, say, against the force of gravity, right? So that would just be the negative of it, right? Yeah, so you can get a negative answer here. It just means that, essentially the force is now in the opposite direction. If you're moving the object this way and the force is the other way, then, right, the force is doing negative work, you're doing positive work. Okay. So either way, don't worry. If you get a negative answer, don't be alarmed, right? That can happen. So that's the idea, right? And this is just a vector field in a plane. We can do one in space as well. You just have a third component to it. Okay. next example, and I think this is an easy one, at least I hope it is. So the vector field f is x squared I plus x times yj. C is the top half of the unit circle oriented counterclockwise, and I gave you a little diagram of that here, right? So it's the unit circle, but it's only the top half of it, and we're going counterclockwise as usual. So evaluate the line integral of f over that curve. Okay, so again, they didn't exactly give us the parameterization for this curve, although it's one that we've done many times before, so I'm hoping by now, remember the radius is 1, right? That's what makes it the unit circle. So if we're going counterclockwise, how about the usual cosine of t for x and the sine of t for y, right? And because we're only going halfway around the circle, t will go from 0 to pi instead of 0 to 2 pi, right? And we'll need the derivative, but the derivative of cosine is negative sine, and the derivative of sine is cosine. Okay, yep, and we don't need the acceleration, right? But you can take the second derivative here too. All right, so yeah, so my dr, right, will just be this vector negative sine t cosine t times dt. Right, and what's f going to be here? So f as a function of x and y is given, right, x squared and then xy, but in terms of t, well, x squared is going to be cosine squared of t, right? And then x times y is going to be cosine times sine, or if it's okay with you, how about sine times cosine, right? So again, all I did was rewrite the x squared and the xy in terms of t, right? So instead of writing the vector field in terms of x and y, we now have it in terms of t. So now we can evaluate this line integral the usual way. T goes from 0 to pi. F is the vector, again, I'll use the bracket notation if that's okay, right? Cosine squared of t for x, and then sine t cosine t for y. And then the dot product with dr, right? So this is what we calculated earlier. This is dr. It's just going to be negative sine t for x, and then cosine t for y times dt, right? Okay, so before we have any hope of evaluating this definite integral, we need to take the dot product. Remember how that works. Multiply the x's, or the x components, I should say, right? So let's see, that'll be negative sine t times cosine squared t, right? Plus the y components, you multiply those, and you get sine t times cosine is cosine squared of t dt. So what happens when you add these up? Well, this is negative 1, positive 1, sine t cosine squared t, right? This is 0. When you add them up, you just get 0. And of course, when you integrate 0, you get 0, right? I mean, you get a constant, but because you're evaluating that constant, this is c minus c, you just get 0. Okay, so yeah, this line integral is 0. Right, that can happen. Right, like I said, it could be positive, it could be negative, and yes, in some cases, it can be 0. Right, so what does that mean? Right, so the work is 0? I moved this particle along the curve, along the circle, and it didn't take me any effort at all to do that. How can that be? Right, how can it take 0 work? So the issue is I didn't draw the vector field, right? If you draw the vector field, here's what it's going to look like. It's going to point outward from the circle, right? It's pointing, yeah, radially outward, radially this way. And that may not be some of these don't look exactly radial, but you get the idea, right? So the vector field, the force, right, is going to be pointing outward. But we're moving this object, we're moving this particle along the circle. Right? So at each point we're moving it, think about a tangent vector at that point, right? Say at this point right here. In fact, I'll do it over here, right? So the tangent vector points this way, right? And the vector field points, roughly speaking, this way. So how do we describe these vectors? You could say perpendicular. I would say orthogonal, right? But that just means the vectors are perpendicular, right? So you're moving the object in a direction where there is no force. The force is perpendicular to that, right? So it doesn't take any work when they're essentially the component of the force is, perpendicular to the direction you're moving it in, right? Does that kind of make sense? Right? And I know that sort of, maybe it doesn't make sense because you're thinking, well, okay, so I have an object on the floor here, some crate, some box, right? And I want to move it this way, right? So I want to move it, say, from here to here. I have to push it, right? I have to push it. I have to apply a force, and that takes work. But wait a minute, gravity acts straight down at each point. So if I have to push the box, I have to apply a force. I'm doing work, right? It does take work, especially if it's a very heavy box. Then you're doing a lot of work to move it, right? So how can that be, right? If I just said that if the force is perpendicular or orthogonal to the direction of the motion, then the work done is zero. And gravity points straight down. Right? Gravity points, roughly speaking, straight down, right? And I'm moving this horizontally, which is perpendicular to straight down, right? So why does it take work to move an object horizontally when gravity acts vertically? Okay, this is a physics question, right? This is not a math question. So if you can't figure it out, don't worry about it. For those of you who've had physics, you know the answer, right? You know it has, well, it has a little bit to do with gravity, but it has more to do with the fact that the floor is not completely smooth, right? It's not like you're moving, imagine if this were just, a block of ice, right? And it's a very smooth floor. It doesn't take that much work, right? Because there's very little friction. But if it's, say, a cardboard box or, a wooden box, and it's a wooden floor, or, imagine a carpeted floor, there's friction there, right? And the friction acts against the force in the direction of the motion. It acts backwards. So the force that you're pushing here, the box, is overcoming not gravity specifically, but the force of friction. Right? And that acts in the opposite direction, which is not orthogonal, but in fact parallel. And because it's in the opposite direction, that's why it's a negative. The force of friction is doing negative work. You're doing the positive work to move the object from one point to another. Okay. So yeah. Now, what causes the friction, of course, is the weight of the crate. So it does have a little bit to do with gravity. Gravity is pulling down on the box, and that causes what's called a normal force. And that normal force, right, the force of friction will be essentially proportional to that normal force. So yeah, indirectly it does have to do with gravity, but it's not the fact that gravity acts vertically, right, and the normal force acts vertically, but the frictional force acts tangentially, right? So that's why it takes work to move an object, right? If there was no friction, right, then it really wouldn't take work. It would only take work because you have to accelerate the object if you're moving it from one point to another, right? So there is a work that you have to do to overcome, the change in kinetic energy, right? Even if there is no friction. But again, that's for a physics course, so I wouldn't worry about that. Yeah. So again, the line integral here is zero, and yes, the work done is zero, assuming that you're moving along a circle and the force acts orthogonally to the tangent vector at each point. Okay, so I hope we've had enough practice with line integrals. There's plenty others in the homework. And if you don't feel like you have, maybe watch the next video, because we're going to do more of these line integrals in the next video. In fact, we're going to do quite a few of them. The difference being in that all these curves that we've done so far, I think, have been smooth curves. We haven't talked about piecewise smooth curves yet. So in the next video, we'll be doing the same line integrals here, but instead of, over just a circle or a line, it might be, this piece, or maybe a square or a triangle, which is not smooth, but it's piecewise smooth. So that, then you have to divide the curve up into different pieces. We talked about that at the beginning of the video. So that makes it a little more tedious, right? So that's what you have to look forward to in the next section.